Today we're going to talk about what to do when our data is not linear, and we're going to look at what transformations we can use to achieve linearity of our data, specifically looking at logarithmic and power transformations, so dealing with exponential and power models. Let's get started. Before we take a look at transforming data to make it linear, today we're going to be using logarithmic transformations, or natural logs. So it is important to remember a couple of things from Algebra 2. The first is that the natural log of e is 1. The second, the natural log of e to the power of x is x. You might recall from Algebra 2, the natural log, or the log of an exponent, remember it takes that exponent and drops it down in front, so that becomes simply x times the natural log of e. From our first rule here, if the natural log of e is 1, then x times the natural log of e is x, or x times 1 is x. So that's where this comes from. And then the last one that you will use is e to the power of the natural log of x is simply x. Remember, e and natural log are inverse operations. So if I raise e to the power of the natural log of x, the e and the natural log undo one another, leaving me simply with the value of x. We're going to use those at the end of the lesson today to take our transformed equations and use them to make predictions for y. So let's take a look at the exponential and the power model. Remember, an exponential model, here is an example, y equals 1 times 2 to the power of x. In an exponential model, your base is constant and your exponent is your variable. So 2 to the power of x, 3 to the power of x, 2.5 to the power of x, those would all be exponential models, where our base is a number and our exponent is a variable. Well, if I look at this data that follows, in this case, an exponential growth model, I notice that the data is not linear. If we're dealing with nonlinear data and we write a regression equation, that equation is dealing with the linear relationship between x and y. So we need to make some sort of transformation for x or transformation for y to actually make the data linear. The other potential situation we have is a power model. Now on a power model, if you'll notice, your variable is your base and your exponent is a constant. So x squared, x cubed, x to the fourth. So if we're dealing for this example here with a part of an x squared model, then we're dealing with a power model. Again, the data is not linear. So if we're looking at a nonlinear relationship, we have to do some sort of transformation for our input or output, our x or y variables, to achieve linearity. So how do we do that? How do we achieve linearity? Well, if we have an exponential model, we're going to take every x, y point and we're going to transform the y's by taking the natural log of each y value. So now we'll look at a scatter plot of x plotted against natural log for all of the y's. That's what we do if our original model is exponential. If our original model was a power model, then we're going to take every x, y point and we're going to transform both the x variable and the y variable. We're going to take the natural log of each x and the natural log of each y, and we're going to look at the scatter plot of that transformed data. Most of the time, we're going to be dealing in this class with either exponential or power models, which means when we're doing transformations, we're either going to select from exponential transformations, x natural log of y, or power transformations where we take natural log of x and natural log of y. Well, it's really difficult for us to look at a scatter plot, especially if it's a small group of data, and tell the difference between an exponential model and a power model. If you look at the two pictures in your notes, they look very similar. Since we probably don't know which one to perform just by looking at them, we're actually going to perform both. Then we're going to select the model that's best based on the residual plot, the one that has the least pattern, and the correlation coefficient, the one that has the highest R value or the greatest correlation coefficient. So to do this, we're first going to create a new list of natural log of x and natural log of y. We're going to graph first our exponential model, x versus natural log of y, and calculate the least squares regression line and the correlation coefficient. We're going to take a look at the residual plots and the correlation coefficient to identify how good that transformation is. Then we're going to graph natural log of x and natural log of y and calculate the least squares regression line. We're going to take a look at that residual plot, so our x's plotted against our residuals, so natural log of x plotted against the residuals and the correlation coefficient. Then we'll determine which transformation is best, and we'll use that transformation as our least squares regression line or prediction equation. So we're going to go through and look at 2 examples so we can learn how to do this. The first example is data from 1981 on soil erosion. So soil erosion by wind, the problem of soil erosion is faced by farmers all over the world. In the paper, Soil Erosion by Wind from Bare Sandy Plains in Western India, there was a report on the study of the relationship between wind velocity, which was our x, and the soil erosion, which was our y. So in this case, remember, y depends on x, so the soil erosion would depend on the velocity of the wind in this, which is a very dry environment. We're going to take a look at a linear, exponential, and power model, looking at the scatter plot for each, the residual plot for each, the least squares regression line, the r, and the r squared values. So we're going to start with a linear model. In order to take a look at our linear model, we're going to take a look at the x and y values, and we're going to put these in our graphing calculator. We're going to go to List in Spreadsheets and enter the data. So I'm going to go to my TI Inspire graphing calculator. Remember, you have to name each list, so I'm going to name my lists X and Y. And then I'm going to input the data points that you see in your notes. So it might be a good time to either do this with me or to take a moment, pause the video, and come back when you've entered all of the data points in your calculator. And then I will show you how to calculate your scatter plot, your residual plot, and your lines of best fit so that we can compare this data. You do have 14 data points, and when you're entering your y's, it's important to double check that your XY coordinate pairs are correct. All right, now that I've got the data entered into my calculator, I'm going to take a look at a scatter plot. To do that, I'm going to add a data and statistics page, and I'm going to ask the calculator to graph my x versus my y variables. Here is a look at our scatter plot. So we're going to add that to our notes. We're going to look at the scatter plot of this data. So again, take a moment to pause the video and draw this scatter plot in on your notes, trying to draw your scatter plot as accurately as possible. Now the next thing we want to do is create a residual plot. Before we can create a residual plot, we actually have to calculate the least squares regression line so that our calculator will actually calculate the residuals. To do this, we can add a normal calculator page, and then we are going to go to our menu on our calculator, and we are going to select our statistics option. Under statistics, we are going to go to stat calculations, and we're going to select linear regression A plus BX. I'm going to tell the calculator to pick from my drop-down menu that my X list we called X, and my Y list was called Y, and then I'm going to click OK. If you notice, this regression equation is a plus bx, where a is your y-intercept and b is the coefficient in front of x for your slope. You're also given your r squared and your r values that you can put on your notes. The last line says resid ... Your calculator has created a residual list for all of the points. Remember, your residual is your error. It's each actual minus the predicted point, or each y minus y hat. Your calculator has actually created a background list of that I can now use to create a residual plot. So I'm going to add another data and statistics page, and I'm going to plot my x's along the x-axis. And now for my y variable, I'm going to pick stat.resid. This will only appear as a choice once you've done a linear regression calculation. Now, please be aware that the stat.resid I'm picking here is the most recent residual calculation I've done. So I need to do these in order. If your calculator numbers them, then obviously the highest number will be the most recently used residual plot. So I'm going to select stat.resid. Well, in looking at this residual plot, there does appear to be a curvature in my residual plot. So if I look at my linear model, I've got my equation for y hat. Y hat equals 19.8508x minus 282. I've got a strong positive linear relationship between the erosion and the wind velocity. And I've got a r squared value of about 81.57%. But in my original scatter plot, there appears to be a curvature in the data, and in my residual plot, there appears to be a pattern. Since there's a pattern in my residual plot, and a curvature in my scatter plot, the linear model is not appropriate. So we need to find a better model. The first thing we're going to do to try to find a better model is to look at our exponential model, where we take each x paired with the natural log of y. Well, I can have the calculator actually do this calculation for me. If I go back to my list and spreadsheets, I'm going to go to a new list, and I'm going to call this ln of x, telling my calculator I'm taking the natural log of x. On the toolbar, the equals line, I'm going to select that line, and I'm having the calculator take, I'm going to have the calculator take the operation. Oh, I need to delete that, sorry. Got a little typo here. I'm going to select the natural log feature, and I'm going to tell the calculator to take the natural log of my x's, which are in column A. Then I'm going to do the same thing here for a natural log of y column. So I'm going to type ln y. And then on the equals line, I'm going to select the function natural log. My y values are in my b column. So I'm going to tell the calculator to take the natural log of all the b values. Now my calculator is going to enter the data exactly unless there's already a decimal. So if you'll notice, when there's a decimal for x, I get a decimal answer. When there's not a decimal, my calculator gives me an exact answer like natural log of 5. The calculator has actually still done this calculation, so that's not a problem. Now we're going to look for the exponential model. We're going to do a scatter plot of the x's and the natural log of y's. So I'm going to add a data and statistics page, and I'm going to graph my x's along with my natural log of y values. Well, this is certainly a more linear relationship than I saw in my first scatter plot with x and y. Let's calculate now the least squares regression line. We're going to add a calculator page, and again, we're going to go to our linear regression. We're going to tell the calculator now to pick our x's, but for our y values, we're looking at the natural log of y, and we're going to create a linear regression equation for the x natural log of y points. So here is my regression equation. Notice my r squared and my r value. My r value is actually greater, which means this is a better linear fit or a better least squares regression line for the linear relationship of x and natural log of y. And my r squared value is higher as well. Once I've done this, my calculator has calculated a new set of residuals. So now I can go to my data and statistics page and I can graph my x's along with my new stat.resids. Well, there's less pattern in this residual plot. Since there's less pattern in this residual plot, it is a better fit for my data than the original linear model. So let's go back and take a look at our exponential model. For our exponential model, we certainly have more of a linear relationship between x and y, and there does not appear to be much of a pattern in my residual plot. The only thing that might be concerning is there seems to be more error for small values of x or larger residuals, and those tend to get smaller for higher values of x, so that might be something we want to pay attention to. Notice now, though, when we write our least squares regression line, my y's were actually the natural log of y. So instead of being y hat, it's actually the natural log of y hat equals 0.238196x minus my y-intercept. My r value says there is a strong positive linear relationship but between x and natural log of y. So now my linear relationship is actually between the wind and not the soil erosion, but the natural log of soil erosion. And my r squared value for this model is higher than my r squared value for the linear model. And my r value is stronger as well. So this model is a better fit than my linear model. I just don't know if my power model might be the best fit. So let's take a look at our power model. Our power model is going to plot the natural log of x's against the natural log of y. So I'm going to take the natural log of both values. Let's take a look at our power model. We've already calculated the natural log of x and the natural log of y, so we can add a new data and statistics page, and we can simply graph the natural log of x against the natural log of y. Again, this seems to be a pretty good linear fit between those variables. X and y variables didn't have a linear fit, they had a curvature, but natural log of x and natural log of y variables seem to follow a linear model. We can now calculate the regression between natural log of x and natural log of y. Again, we're going to go to our linear regression, only now our x values that we're using are the natural log of the x's, and my y values are the natural log of the y's, and I'm going to create a new linear regression model. Again, this makes my calculator create a new list of residuals. Now let's take a look at our residual plot. We're going to go to data and statistics, but for this plot, our x's were natural log of x, and our y's were our stat.resid. There is my residual plot of my data. So let's put this all together on my slide here. Now we can look at our power model. Well, on our power model, if you'll notice, this does seem to be a strong positive linear relationship between natural log of x and natural log of y. And so if we were interpreting it, we would say there is a strong positive linear relationship between natural log of wind speed and the natural log of soil erosion. I have the highest r squared value of any of my models, and then this is my regression equation. It's a least squares regression line. I'm still picking linear regression, but now my variables are natural log of x and natural log of y. There doesn't appear to be a real pattern in the residual plot. There does appear to be a random scattering of points. There are higher residuals for smaller values of x still, but this is the best model that we've taken a look at. When we're doing regression in a statistics course, we're only looking at linear relationships between variables. So we're not creating on our calculator a power model or an exponential model. We're looking for a linear relationship. So if there's not a linear relationship, we're actually changing the x and y variables to create a linear relationship between the data. In this case, because the residual plot has no pattern, the scatter plot So since the residual plot has no pattern, the scatter plot is linear, and the R value and R squared value are the highest of the models, natural log of y hat equals 4.57865 natural log of x is the least squares regression line, or the line of best fit. This is the best model. All right, so how do we use this? Let's take a look at another example so that we can look on how best to use the model. In this data, we wanted to look at whether the range of flight can be predicted by the speed an airplane travels. The data graphed is below is from a table called Aircraft Operating Statistics from 1997 in the World Almanac and Book of Facts. So if you notice, we've graphed our speed as our x value in knots, and our y value is the range of the aircraft. So we're looking at whether or not we can predict the range of the aircraft based on the speed, or we're looking at the relationship where range in nautical miles depends on the speed in knots the aircraft traveled. If we look at the scatter plot, we notice that there appears to be a curve in our scatter plot. We also notice there appears to be a curve or a pattern in our residuals. So the answer to part A, look at the scatter plot and the residual, is a linear relationship appropriate? The answer would be no. Since there is a curve in both the scatter plot and residual plots, a linear relationship is not appropriate. Remember, if we're looking at a residual plot, we want to see no pattern, no curvature or no megaphone, no pattern in our residual plot. When there's no pattern, it tells us a linear model is best. Well, in this example, we've gone through and we've actually taken a look side by side here. The first model on the left is where we've used speed with natural log of range. The second model on the right, we've taken both the natural log of speed and the natural log of range. Looking at both scatter plots, there does appear to be a linear relationship between those variables. Looking at the residual plots, they're nearly identical. There doesn't seem to be a difference in the residual plots, but there is a more random scattering of points on this residual plot than there was for the original linear model. So what we can say is that either transformation could be used as acceptable. They both have very high R squared values, so either models, because the scatter plots are linear, the residual plots have a random scattering of points, and there is a high R squared and R value, either model could be appropriate. Well, let's first start by looking at the exponential model. When we take a look at the exponential model, we're taking a look at the natural log of range hat, or natural log of y hat, equals 0.0137 times the speed plus 0.79. Well, let's actually use this exponential model to predict the range if the speed is 500 knots. Well, speed is my x. So natural log of range hat is equal to 0.0137 times my speed, which was 500 knots, plus 0.79. If I enter this into my calculator, my natural log of range hat would be 7.64. Well, that doesn't mean that I have a range of 7.64 nautical miles. It means the natural log of that predicted range is 7.64 nautical miles. I don't want the natural log of the range. I want to take this back to the original units of the problem, which was simply range. Well, if you'll recall from our very first slide on Algebra 2 review, if I take a look at e to the natural log of y, or e to the natural log of x, I simply get, let's write this up here, e to the natural log of x is simply going to give me x. I also know that I can do the same thing to each side of my equation. So I can raise both sides as a power for e. E to the natural log of range equals e to the 7.64 power. E and natural log are inverses. They cancel one another. So I get my range hat is e to the power of 7.64 or 2079.74 nautical miles. We always have to go back using our transformed equation to the original units. Now let's take a look at how this would work for the power model. For the power model, I'm taking a look at the natural log of range hat, which is equal to 6.105 times the natural log of speed, which would be 500 minus 30.3. Putting this into my calculator, the natural log of range predicted is going to be 7.64018. Again, e to the natural log of range would be e to the 7.64018 power, or my range predicted value would be 2080.12 nautical miles. Now, we said that either model is appropriate and we can use either one. Their scatter plots and residual plots are almost identical. We could go ahead and decide, because of the higher r-squared value, maybe we would prefer to use an exponential model. Well, there you've learned about transforming your variables for x and y in order to achieve linearity. Let me know if you've got any questions.